Previously, we looked a little bit at a little more of the graphing type aspect of kinematics and stuff like that, and how we could expand on a few things compared to what you did last year. I mean, if you go back, just quick little thing here. For example, last year, you had the classic, distance time type thing, and of course the slope was equal to the speed. You guys even did stuff like, if you had distance time graphs and, you did curves and stuff like that. And what you guys would do is, make tangents, right? And then so you guys would use the tangent slope, and that would give you your instantaneous speed. And then and the same thing with the VT graph. The slope would give you your acceleration, and the tangent on a VT graph would give you the instantaneous acceleration. So what I showed you last time is it goes a little bit beyond that, where if you have especially a VT graph of some kind, and it doesn't really matter what it looks like, but it was the area. So areas can also be used to find different values, and of course the area here was the change in distance, or the distance it went, and of course the area on an AT graph would give you the change in V. So it's really neat. So it's not just always about slopes, but it's also about areas. So we're going to use that idea and expand a little bit on your kinematics knowledge into more grade 12 kinematics using this idea. So what I'm going to do is I'm going to make just a basic sketch of a graph, a nice little VT graph, and I'm going to, I'll use my tool here, something like this. So a nice straight line VT graph, something like that, where it's not starting at 0. So this is a V1. This can be V2 out here, and of course from here to here would be your delta t, something like that. Okay, so nice constant acceleration. So that's we're kind of restricting here. So we're gonna have nice constant acceleration, and the first v is not necessarily, it could be equal to 0, but it's just going to say it's not equal to 0. So we're going to do something like this. So what if we want to know how far it went? Well, that's pretty simple. DTV, you would just do something like this, where you would use the average speed and multiply by the time. Now, of course, you guys also know now that it would also be equal to the area underneath, and you'd have the area of this triangle and the area of a rectangle. Now, the situation we've actually set up is kind of actually pretty generic. I mean, V1 could be equal to 0, V2 could be equal to 0, it could go up, go down, but we're looking more of an overall generalization of what's going on. And of course, I mean, we talked about this before, I mean, this would be the area underneath the graph. And there's a couple things you can actually do with that. For example, you have two areas. You've got the rectangle as well as the triangle. And of course, the area of the rectangle would be, if we did the rectangle area, the area would be the base times the height, which is the t times the v1, and that's basically dtv. And if you did the triangle part, the area would be the base times height divided by 2, and the base, of course, is time. The height of that triangle, it's not v2, it's actually v2 minus v1, v2 minus v1, and base times height divided by 2, something like that. And you can sort of recognize it a little bit right here. This right here, if you actually did that, it'd be the combination of those two things put together divided by 2. If you sort of take these two and incorporate them together, you can actually get some of your classic expressions that you had last year. For example, if we sort of like the total area, if we did the total area all together, that would be TV1 plus t times v2 minus v1 all over 2. Now what I'm going to do is I'm going to sort of multiply this out a little bit, bring the 1/2 in front. We're going to sort of mess around with this a little bit, but if we would sort of piece this together, and we know this is going to be equal to dtv. So if I do this, I'm going to do a little algebra, show you some of your classic stuff comes from. Well, first of all, I've got a t in each part, so I'm just going to cancel it out. And if I cancel it out, I got the average v is equal to, and I can sort of like ignore this part in the middle here, v1 plus v2 minus v1 divided by 2. Now, if I sort of multiply that 1/2 out here, I've got the v1 plus v2 divided by 2 take away v1 divided by 2. All right, now if I sort of piece this together, I've got a v1 take away half of v1, which leaves me with half of v1. So this is going to be v1 divided by 2 plus v2 divided by 2, which is v1 plus v2 divided by 2. So just this little quick little thing here, but just this alone, average v is equal to v1 plus v2 divided by 2. Now, of course, you're going dub and using that all through grade 11, which is true, but it sort of shows where this actually comes from, the idea behind it, how things all link together. And it's not just random number stuff. Graphically, it all gets tied together, okay? But now let's do something a little bit different with the graph we're looking at over here. We're going to look at this a little bit more. The v1's arbitrary, the v2's arbitrary. We're sort of like a general expression going on here, okay? So we're going to build up a little bit something here. So I'm going to start with the basic DTV, okay? Good old DTV, something like this. Now, what I'm going to do is instead of using the average V, what I'm going to do is I'm going to incorporate what we have right here. So instead of average V, what I'm going to do is I'm going to put in the T, and I'm going to put the V1 plus V2 divided by 2 instead. Okay, something like that. Now what I'm going to do is I'm going to multiply with the brackets. So I'm going to multiply with those brackets, and we'll crack the 1/2 out in front. So you basically have 1/2 T V1 plus 1/2 T V2. Okay, good old basic algebra type garbage. All right, now we're going to do something else here. I'm going to incorporate something else you guys also had from last year. From last year you had change in V, which is acceleration times time, of course. And in the situation we have here, if I wanted to know my new speed, if I wanted my final V, what I can do, if I go back to this generic situation over here, my second V would be equal to my first V plus my change in V. But that would then be equal to V1 plus acceleration times time, because change in V, of course, is acceleration times time. Well, I can use this idea here and substitute over there. So this would be 1/2 T V1 plus 1/2 T, and this would then be V1 plus acceleration times time. Now this looks like a bit of a disaster going on, a little bit of a mess, but we're going to try and clean this up a little bit as well and sort of show you how the stuff pieced together. Now it's really common typically to know V1. It's not very common to know V2, usually trying to get to that V2. So trying to get substitute out for the V2 and having the V1 plus AT is a little bit nicer. Okay, all right, now let's just clean this up a little bit. I'm gonna get rid of those brackets. And if this can stay the same, 1/2 T V1. I'm gonna multiply with the brackets. So I'd have 1/2 T V1 plus 1/2 T squared times A. So I got something that looks like this. Now I have a 1/2 TV1 plus 1/2 a TV1. So that would come together to make a whole TV1. These two combine together. So that's going to be T times V1 plus, and I'm going to move around this a little bit, because usually you have the polynomials, you try and have the higher powers later on and stuff like this. I'm going to move around something like this. All right. So we have this. So TV1 plus 1/2 AT squared. Now, this is kind of a neat expression, because if I go back to the beginning, this is all starting with D. So this is D is equal to this. And what's nice about this is now we have two variables together we haven't had together before, and that is D and A. You know, you had DTV and you had VAT, but no distance and acceleration tied together. But this one actually ties them together. And if we sort of make this even more general, what if your first distance wasn't equal to 0? Sometimes you'll see it written as the delta D, which of course is just D2 minus D1. Well, if I write it like this, I can incorporate this onto the other side. You'd end up with D2 is equal to D1 plus, and I'm going to move this around because usually the T's are last on both of them, V1T plus 1/2 AT squared, something like this. So this right here, it looks like it's a big kinematics equation, but the great thing about this kinematics equation is it's got pretty much every variable or every quantity you could possibly imagine. It's got D's, V's, T's, and it has acceleration. It's got the A's in there as well. And it's a great expression. Now, it's way bigger than just DTV and VAT, but it was the DTV and VAT that were sort of spliced together to actually create this expression. Now, this is like one of the major kinematic questions or equations used in all of physics and stuff like that. So it's a really, really important type of formula. Now, the great part about it, a lot of the time, yeah, so often these things are often equal to 0. For example, D1, if you're at the origin, D1 is equal to 0. If you're starting at rest, V1 is equal to 0, and both these terms can disappear. If you have no acceleration, then this entire term is equal to 0, and all you're really left with is basic DTV. So it looks like a really, really big formula. It's kind of complicated, but the nice thing is often a lot of the things end up being zeros and you don't even need them, and it shrinks right down to something much more small, much more manageable. But it's a great expression because it ties lots of quantities together, so it's way more versatile than just basic DTV and VAT, and it's a lot tighter and works a lot better. Okay, so we're going to practice using this a little bit and sort of show you how this works. Okay, so let's take something really simple. So like here you got a car or something like that. You're going to draw a little car and just show how nice this expression can be. All right, so a little car, and let's just say it is starting at rest. Nice and basic and simple. So starting at rest, blah, blah, blah. And what it's going to do is it's going to accelerate at 1.75 meters per second squared for, let's go with 5 seconds. Okay, so how far did it go? Well, you could have done this last year. If you'd have done this last year, basic grade 11, and there's still nothing wrong with this. You would have something like, do delta V is acceleration times time. You would have taken this to find out the average V, and then you would have taken this and used DTV in order to find out how fast it's going. So sort of like 3 steps. Well, if we go to this giant equation, I often call it the mother equation because it like gives birth to a whole bunch of stuff that you can do with it and stuff like that. If I jump to that equation instead, and you'll often see it written as D2 equals D1 plus V1t plus 1/2 AT squared, well, I really don't need the entire thing. D1 is equal to 0, so that's gone. V1 is equal to 0, so that term is gone. All I've got is 1/2 AT squared, which is a great part of this expression for lots of different things. And if I just use the 1/2 AT squared, I can calculate how far the car went. So I've got that 0.5 for the 1/2. I'll times that by the 1.75, and then I will times by the 5. Don't forget to square the 5 seconds. And I put that all together. We'll round off a little bit. We're looking around 22 meters altogether. Okay. So by doing this, it's quicker than doing VAT, cutting in half, and then DTVing it. There's also less error because you got 1 calculation instead of 3 calculations. So there's less error with rounding, and you get more precision and more consistency. Okay, so let's try something similar. What if instead the car, take the exact same car, let's say instead it started, at, let's go with 4 meters per second. And let's do the exact same thing. So how far did it go? Okay, let's do something similar. Well, if I did that instead, D1 still equal to 0. I'm not even going to bother writing it down. So it would just be, final D, D2, just overall D would just be V1t plus 1/2 AT squared, because now my V1 isn't equal to 0. So if I do that, my V1 is the 4, that's the initial V. The time is still 5 seconds, and then I'll do the 1/2 AT squared all over again, which is still going to be the 22. So this is, of course, 20 meters there. If I do 1/2 AT squared, it's still the same acceleration, it's still the same time, it's still going to give me that 22. I've got something like this, so then my total distance would be 42 meters. And again, if you could have done this last year, it would have been find the change in V, add that change in V to the initial V to find your final V, then average out your initial V and your final V to get your average V, and then DTV. So again, it'll still work that way, but this is way quicker, way more accurate, way more consistent. Okay, it works really nicely. Okay, Let's modify the situation again. Okay, let's take the exact same car. Let's change it up again. What if instead it started at a different speed? So it's not going to start at 4 meters per second. Let's start at something else. Let's say it started at 15 meters per second, and instead of going faster, what if it slowed down at 1.75 meters per second squared for 5 seconds? Okay, so starting at 15, and let's have the car slow down instead of speeding up. Okay, well, again, it's gonna be similar. Okay, we've got the d2 is equal to v1t plus 1/2 at squared. D1's often equal to 0. It often never really comes into play. And sometimes it can, but whatever. So for this one here, I've got my v1 would be the 15, and it's still 5 seconds, plus 1/2. Now this is where you got to be a little bit more careful, because the acceleration, since it's slowing down, the acceleration is going to be negative. So it's going to be negative 1.75 times the 5 squared. Okay, so that's where the key, you got to be careful with that part. That's where the key kicks in. It's a great formula, but you got to be a little bit careful with positive negatives when things are slowing down and stuff like that a little bit. Okay, but then once you have this, it's very much the same type of thing. I got the 15 times 5, which of course is going to give me 75. And I'm going to add this part. Now, of course, I didn't change any numbers. It's still going to end up being 22 again, except instead of positive 22, it's going to be negative 22. Okay, so I've got 75, and then basically subtract 22, which will leave me with 53 meters. Okay, so again, you could have done this last year in grade 11, but it's going to take you like 4 or 5 steps, and here you're doing it in 1. Now, especially when you're starting using this expression, I highly, highly, highly recommend calculate the first chunk, write it down. Calculate the second chunk, write it down, then add them. Same thing here. Calculate the first chunk, calculate the second chunk, write them down individually, and then put them together. Okay, it'll help to catch little errors and stuff like that. Okay, also one of the more common mistakes is forgetting the squared. Don't forget the squared. And it's not the entire thing squared, it's just the t that is squared. So you also got to be careful with that as well. Okay, so that's how this expression can work. All right, so let's look at some other stuff and some more practice with it. All right, so let's try another scenario. So, all right, so got some grass, maybe got a guy over here, getting ready to run. Now we'll just have him starting at rest, no big deal. So he's just starting at rest, something like that. And he takes off, okay? And let's say he can accelerate at 0.65 meters per second squared, okay? So how long would it take for him to go? Let's say 8 meters. Okay, so we're looking for how long it would take him to go 8 meters. Now, last year, this has been really challenging because you've got acceleration, you've got distance, and you're looking for time. You didn't really have an expression that tied those 3 things together. Well, now you do. So if we go back to the jumbo equation, the mother equation, you know, D1 is equal to 0, so done. V1 is equal to 0, done. The only thing I'm left with is that last part, distance is 1/2 at squared. And this is a really, really awesome little chunk to use from this expression. It comes in handy for lots of different things. So in this case, I'm looking for the time. So if I rearrange this for t, it'd be 2d divided by a, and then don't forget a square root. Okay, so multiply by 2 on both sides, divide by the a, and then root it to get your answer. So I've got 2 times the 8, of course, that's 16. And we divide that by the acceleration. Do not forget to square root. And if I do that, it would take, well, give or take about 5 seconds for him to go those 8 meters. Okay, works really nicely with a little chunk of 1/2 at squared. There's lots of different things we can actually do with that. Okay, so let's try something else as well. Suppose, do some grass again, draw a little tree or something like that. Okay, let me merge that. Something like this. Okay, and let's say We got some kind of furry little creature, and it falls out of the tree, something like that. And let's say it falls down, and let's say it falls for 1.45 seconds. Okay, so it falls for 1.45 seconds. So how far did it fall? Okay, really simple. Again, the 1/2 AT squared works really, really nicely for this. So distance would be equal to 1/2 AT squared. Now, the only thing is, what is the acceleration? Well, what's pulling them down? Well, that's just gravity. Okay, so you just got to throw in your acceleration due to gravity for the free fall. Now, of course, that's good old-fashioned 9.81 from grade 11. And then you've got the 1.45 squared. So again, the 1/2 AT squared works really, really, really nicely, even for things that are falling down. So you got that 0.5, you've got that 9.81 for gravity, and then you've got that 1.45, and don't forget to square that. And well, just over 10 meters. Looks like it fell about 10.3 meters. Okay, so once again, that 1/2 AT squared works really, really, really nicely. Okay, let's try something else. Well, let's do something with a little more gravity again. Okay, because gravity is a common acceleration to cause things to move. So how about something like this? What if, there's some ground or something like that? And let's get a person there. Okay, and there she is. Something like that. Okay. And maybe she has something really simple. We'll give her a little apple. Classic physics type apple. And what she does is she's going to throw that apple straight up. Okay, so she's going to throw that apple straight up. And let's say she throws it straight up at, let's go with 4.8 meters per second. Okay, and let's take it one step at a time. So let's go with this. Let's start with this. How far has the apple gone after, let's just go even just after 0.75 seconds. So how far has the apple gone after just 0.75 seconds? Okay, well, let's see. Let's work with this a little bit. I will crack out the big expression. D2 is equal to D1. D1, I can make that equal to 0. I can choose any reference frame I want, and I'll use her hand as 0. So that's no problem. So V1t plus 1/2 AT squared. All right. So V1, well, that would be the 4.8. And the time, of course, is the 0.75 plus 1/2. And now I've got my acceleration. Remember, gravity is involved again. And gravity is slowing it down. So instead of just putting 9.81, I'm going to put negative 9.81. And then I got that 0.75 squared into there as well. So we're going to calculate this out. And again, I recommend punching each one out separately, each chunk. So the first part, we got the 4.8 times 0.75. That's just going to be 3.6. And then if I multiply the rest, I've got the 1/2 times the 9.81 times the 0.75. And that part, of course, is squared. And it'll end up being negative because of the negative 9.81. So I'll subtract we'll round off to the same sig figs, 2.8. Okay, so I've got 3.6 take away 2.8, so that would be basically just not 0.6, about 0.8 meters, and that's how far it has gone. So that would be how far it's gone from her hand. That is my reference point. So if I change the question, and maybe I knew that her hand was 1.5 meters off the ground, and the question was how far from the ground, you could do the exact same thing, except what some people would do is they would do D2 is equal to D1 plus V1t plus 1/2 AT squared, done the exact same calculation for this part, and then that part right there would be the 1.5. Some people will just do this entire calculation like we just did, and then just add the 1.5 afterwards, and you'd still end up with 2.3 meters. It doesn't make any difference how you do it. People see things differently. It doesn't matter. but it's still going to work out pretty nicely. Okay, so this is just in practice with this bigger equation. Again, you can use DTV and VAT all the time. This one just becomes a little more efficient, a little more effective, a little more consistent than doing other ones like the DT and VAT, where you round off, more chance for error and stuff like that. Okay, let's try one more question. All right, so let's say, here we go. Got like a rocket. So fire going at the back. There we go. Got some yellow in there. There we go. And why not here? Got some crazy guy riding the rocket. There you go, something like that. Okay, good. All right, now let's say the rocket's traveling along, and let's say the rocket is traveling at 50 meters per second for 3.5 seconds. And then what it's going to do is it's going to start like running out of gas and stuff like that. So then it's going to slow down. It's going to slow down at 4.8 meters per second squared for, let's just go with 2.6 seconds. And I want to know here, let's do how far again. Good old how far. Okay, something like this. All right, so there's a difference between the other questions we're practicing and this one. This one cannot be done in one calculation. It's not possible. This one minimum has to have 2 calculations. That's why I do 2 arrows, like a hint type thing right there. Now, the reason I know that is because there's different things going on. Now, some people say, well, there's 2 parts because there's 2 times. Well, it's actually not really about the times. That's not really the key. The key is about how many accelerations there are. In the first part, the acceleration is equal to 0. In the second part, the acceleration is equal to 4.8. In fact, it's actually negative 4.8. That tells me that there's 2 parts, is how many accelerations there are. So the number of accelerations, that tells you how many parts there are. Okay, often it's the times, but it doesn't have to be. It's actually about the accelerations. And the reason is, if we went graphically, like go back to the graph, it looks something like this. And every time that the graph changes direction, there's different chunks, so different calculation. Okay, so whenever you have multiple accelerations, and it could be 0, there's different parts. Okay, so we just got to take it one part at a time. So for the first part's easy. The acceleration is equal to 0. It's just constant motion. That's easy. So my distance here, I'm going to call it my first distance, is just basic DTV. That's all it is. Just a constant speed. It's going 50 for 3.5. No big deal. That's it. So I want to calculate that first. So I've got the 3.5, and I'll multiply that by the 50, and we get 175 meters. Okay, that part is done. Now I'm going to go to the second part. So for this one, D2 is equal to D1. Now for D1, you can just leave it empty if you want, or you could use the 175. It doesn't make any difference. You can incorporate it before. I like to incorporate it afterwards. I just want to find out the distance for the second part. So if I do that, I've got the D2, and I've got the V1t plus 1/2 AT squared. Okay, so my V1 is 50, starting at 50 meters per second during the party. That's the 50 from the beginning. It's going 50 meters per second. Now, which time do I use? Well, I only want the time for the second part. The 3.5 seconds has nothing to do with this. I'm going to use the 2.6. Keep the parts separate. So I got my plus 1/2. My acceleration is 4.8, but since he's slowing down, it's going to be negative 4.8. And then my time again is the 2.6 squared. So don't mix pieces together. The 3.5 and the 2.6 seconds are totally separate things. The 4.8 only exists in the second part. There's like a little boundary between the two. The only reason I was able to use the 50, which is like first part information, in the second part is because when you start the second part, he's still going 50 meters per second. Okay, and that's why I'm able to incorporate it. Okay, so now let's calculate this. I've got the 50, and I'm going to times that by the 2.6, and that chunk right there is 130. All right, so now I've got the rest of this thing. I've got the 1/2, and I've got the 4.8, and I've got the 2.6 squared, and I know it's slowing down, so it's going to be negative. So I'm going to subtract that. So we'll just say 16 meters for now, something like that. So if I got the 130, take away the 16, that's 114 meters. So I just got to put the two things together. During just the first part here, went 175. During the second part, went 114. Now I'm just going to tie those two things together, and I get a total distance of 289 meters altogether. Okay, so it's a great equation, can really tighten things up, make things more efficient, but if you change accelerations, if the motion changes based on acceleration, you got to do more calculations. So this would be a minimum 2. You could do it more. Like you can use DTV and VAT through the entire thing. It's going to take you longer, but it can also work perfectly fine. So this is just more practice, and of course this equation will be used over and over again, and we'll do some more practice and tie things together and show some other expressions as well. But this is a great equation that can be used for lots of different things.